schematic diagram, assuming that happen in real sense in experiment, and how the microstructure evolved during the solidification process. So in A point, this is your A point. Okay, so the temperature is roughly 1300 degrees Celsius. Okay, so your material is basically in liquid state. So the liquid composition, the composition generally which you choose for alloy is represented by C naught. It means the composition of liquid. Okay, your composition of liquid. Okay, that will equal to what? Original composition of alloy. So alloy composition of that is basically C naught in liquid, and it is a single phase region. और degree of freedom निकालना है in that region, then F is equal to C plus P, so C minus P plus 1. Because pressure we consider 1 atmosphere, so your parameter in place of 2 I'm taking 1. Okay, so in single phase region, number of component is basically 2, number of phase is basically 1 plus 1. So degree of freedom is how much? 1. Sorry, number of phases is, sorry, I returned wrong. The number of phases is 1 single. Okay, so the degree of freedom is 2. What it means? I can change composition or independently, that will remain even liquid only. If I change temperature also, that also remain liquid only. So single phase hi rahega. So I can vary my parameters independently, composition and temperature, and your phase doesn't change. It will remain single phase only. So you can see here. So like either I choose this composition or this composition. In this region, this will remain in liquid region. It will remain liquid only. Temperature I will change that this one, the 1200 I take, sorry, 1350 I can take, 1400 I take, 1310 I can take. You choose any temperature in this region. Temperature भी कोई भी लो, चाहे यहाँ लो, चाहे इधर लो, चाहे इधर लो, चाहे इधर लो. Anywhere you take in this liquid region in single phase, your degree, you can independently vary your composition and temperature. Okay, so we have a freedom both. Okay, now that's the reason the composition of liquid will be the same what is the composition of alloy. 30. So in that liquid we have a 35% nickel. Okay, now you cool down. Now I have cooled down, and from temperature this A to I reach B. Okay, I reach at B point, and B point is a this line we call, which is separating two phase region, alpha plus liquid and liquid. That boundary we call a liquidus boundary, and the boundary between 1,2 phase region and solid alpha, so that boundary we call a solidus boundary. Okay, and the tie line we use to identify the compositions. Now we reach point B. Okay, so we reach point B, and correspond to this, that is a temperature. Somewhere I can say 1270 degrees Celsius. Okay, at B point. At B point is the point where your solidification just start. When you touch that boundary, I assume solidification just starts. So clusters just grow or nucleate from the material. So this basically, these are in diagram you can see here. This irregular shapes are shown here. So they are basically alpha particles nucleated in liquid. I'm not drawing that one because this is already there in the this picture. Okay, this image, it is already there. Now I have written here liquid has a 35 weight% nickel and alpha has 46 weight% nickel. Why? How? So that is information we'll get from the lever rule. So lever rule is that from that point, that temperature, I'll draw a line. This blue color line I have drawn. I am drawing over it red color. Okay. Now one side touching my liquidus, one side is touching my solidus. So from there, if I draw a line below, and it will cut somewhere here in my x-axis. X-axis represent my composition. So this composition is basically now roughly 46 weight%. So this is a composition of solid, which gives the composition of solid is what? 46 weight% nickel. So from tie line I find out, and this boundary, okay. So this boundary I'll touch. This is my alloy composition also. So this is my 35 weight%. So liquid की composition कितना? Liquid has a 35 weight% nickel, and solid is alpha is 46. In alpha, we have a nickel is more. Okay. Now, if you see carefully, nickel has the highest melting point. Okay. So it means nickel atom will come as cluster first compared to copper one. Okay. Because while cooling down, first nickel will atoms will come. Then copper has a lower melting point. As a, okay. Now this is the how microstructure boundary will evolve. Now let's come down to C point. Now this C point, this temperature I can say this is the temperature 1250 around. Okay. Now I could see here my alpha particles, they have grown up. Okay. They have grown up, and still I have a liquid because it's a two-phase region. And in liquid, my composition, we have a 32 weight% nickel in liquid, and you can see 68 weight% copper is there. Alpha, we have a 43% nickel. Okay. Rest is copper. So how I know this is 43 and 32? For that, I have drawn a tie line again. Tie line method, this one I have already explained above. Same method I'll utilize here. This is from here to here, I'll see. So it is cutting at liquidus here. Okay. So this is my liquid composition, 32 weight% nickel. Okay. And this is my solid composition. In solid, nickel is how much? 43. आप देख सकते हैं draw करके. Now, if I have to ask you what is their amount is present, how much? Composition I know what is the amount, but so then I'll apply a lever rule. Lever rule, you measure this composition difference and this composition difference. Okay. So liquid कितने percent है और solid कितना percent है? Lever rule have to apply. So lever rule will apply and see the phase fraction. Okay. So we'll measure the phase fraction or weight fraction. Okay. Of liquid. Let's say liquid WL will निकालना है. So that will is equal to okay, WL. So that will equal to I will calculate C alpha. Okay, C alpha minus C naught divided by C alpha minus C L. This formula I'll use. I have already explained this formula too, if you remember in my previous lecture. Okay. So this formula I can see if you apply, so that will is equal to 43 minus 35 divided by 43 minus 32. So that is equal to 8 divided by 11. So you can divide this one, then that will give the phase fraction of liquid. Okay, so that is roughly 0.72. Okay, now अगर मुझे solid की निकालना है, phase fraction of solid, that is equal to I represent by or W alpha, that is equal to roughly निकालोगे तो that formula will be here is and C naught minus CL, so that is basically 35 minus 32 divided by 43 minus 32, so that is equal to 3 divided by 11. Okay, 3 divided by 11. So I am using my mobile calculator. So at this stage, like it is easy also, no problem. We are not good in now. We dependent upon calculators. 2.27. Now, roughly this one also I can say It is some other, but could go down figure. I put 3 also. I should put 3 here. So 0.073, 0.027. Okay. The addition of this one is basically W liquid plus WA, that is alpha is equal to 1. So no need to find out other one. If you know one in phase fraction, you can just subtract 1 minus that phase fraction, it will give the second one. So this way I will know how much. So I can say in this case, at this temperature, it is 73% liquid is present and 27% solid is present. Okay. So how much in percentage you have to say liquid is present? 73% liquid. And this one is how much? 27% solid present. So this one is at what temperature? 1250 degree Celsius. So this kind of numerical problems you can expect in your quiz also. Okay. Calculate the phase reaction. So something like that, or it may be EST exam. So we have dealt with now this problem. Now from there I cool down, I reach D point. And as D point, ideally liquid should be very small. Major places I should have alpha grains on, alpha particles only at D point. So this is the temperature. Okay. Composition निकालना है, liquid कितना है? This is my composition of liquid. Tylines 22% nickel. And solid is how much? So in solid, I have a alpha nickel is 35%. That is my actual original one, alloy composition I've taken. So, and macrostructure is like this. When you reach E point, that is well below from solidus, like 1180 degrees Celsius, 90 degrees Celsius, your completely liquid is completely changed into solid, and we have a alpha. So at E point, no need timeline, just the composition of solid is equal to composition of alloy. So we have a copper 35% nickel. So this way I can choose this alloy composition also. 50 वाले भी ले सकते हो. Here also in exam we'll ask you, there is a isomorphous phase diagram in germanium silicon. Please draw, explain the microstructure development at 1250 degree. So actual microstructure development for alloy composition, where we have chosen silicon 35% or 68% silicon and 48% germanium. Then you have to show systematically symmetric diagram. One point you should take in liquid region, 1 point you take on solid liquidus, 1 point you should take in two phase region, 1 point you take on solidus case, and 1 point is solid. So total 5 point you see, you write and draw this symmetric diagram and explain it. Okay. And if you write the composition, that will be great if you know the composition, like here is written. Okay. So that is about how the microstructure get developed during equilibrium cooling, when cooling rate is very slow and you're giving enough time atoms to go and diffuse, or diffusion time is enough. So they take their respective positions. Okay. Now we move to the next one. If any one of you doubt here, you can ask me. Okay. Because I'm not asking a counter questions, because many times you don't answer. Like okay. Now we'll see a case how the macrostructure get developed, evolved during non-equilibrium cooling. Non-equilibrium cooling is fast cooling. It means that does not allow phase equilibrium to maintain during the cooling process. In that case, we are phase equilibrium we are maintaining. Here we are not giving atoms enough time. Okay. So we have heterogeneity in the microstructure, the compositional change when it solidifies. So cooling rate is much greater than diffusion time. So it's called non-equilibrium cooling. It means from melt directly I'm quenching. So that occur, like if cooling slow, no equilibrium cooling, we are taking 10 minutes for cool down. Here I am doing in fraction 30 seconds and 50 seconds. Just suddenly, very fast. Okay. So sometimes we have advantage, some microstructure such kind of cooling, and sometimes we have disadvantage also. So in case of isomorphous, we have disadvantage. Let's see how. Now, same way, this is my phase diagram, and copper nickel same alloy I have taken. Our alloy composition is also same. Copper 35.8% nickel. Only slightly change. You will see I drawn a dotted line here. Okay. So what we believe the material is basically solidus generally shift from its actual position. Okay. So that represented by the solidus line. And same we have drawn this line, dotted line you can see here, and we have chosen prime points A prime that is in liquid, B prime in liquidus, C prime in two-phase region, D prime in basically on D prime we have taken in solidus, and E prime we taken new solidus case. Okay, this one dotted line E prime and F prime. So 6 point we have taken here. So cooling rate is very fast. So cooling rate is very fast. It means the why I'm saying this one. This force to solid should form here 12-20 degrees Celsius. But we are cooling fast. So where temperature has dropped from not 1220, 1220 cross very fast. It is basically here 1205. The actual temperature has just lower. Cooling is very fast. Or it's other way around. Okay, just lower. Now at A prime is this in liquid state, single phase, no problem. It will behave like equilibrium cooling only. So that's the reason you have a liquid, and this one liquid, and liquid has a composition which is the composition of alloy liquid copper. We have 65.8% and 35.8% nickel. So at B prime also no issue at all, because B prime also this is solidification just started. We have a nickel 35.8% and alpha is again tie line temperature of 46, and this one is again alloy composition 35. So liquid is 35 and alpha is 46.8% nickel. Okay, now problems come downward. Okay, when you reach point C prime, so at C prime your alpha first nucleated which is 46.8%. Okay, now here your alpha, okay, alpha now here tie line is joined. This is the line now. So tie line, this is the where it's touching solidus. This is another solid. Two solidus are there. So I can say this one solidus represent 42, one solidus represent 40. So as per diagram, so it means the first alpha is 46%. Now second alpha which is grown, that is depleted in nickel. So composition basically that will have a 46%. So it start making a kind of a core structure. Okay, so core structure means like first one is alpha. So we have this one. I'll put the other way around. So this is my 48%, and then in that I have a 46. So green color represents 46. So inner alpha which is nucleated first, that has a different composition 46. Now outer one, this is 48% nickel liquidus, this one. Okay, so now if you come further, so there is a decrease in alpha from, you're going from center to this side, your alpha will decrease in this direction. Okay, from center in alpha grains basically. So now when I reach at D prime, okay, at D prime, my D prime, the actual liquidus composition is supposed to be 38% nickel, but in liquidus is touching, solidus point is touching at 35.8%. So the alpha which is now from C to D prime, the alpha which is solidify, which will grow, that will have how much nickel? 35. Initially we have a 46 and 40, then 35. Where liquid, no problem, liquid 24 weight percent only. Okay, so now you can see here also three colors clearly. Inner one has 46, then outer one little darker, lighter, that will has 40, and outer lightest one has a 35%. Now E prime. Okay. At E prime, here is most of places you have a solid only. Okay. So we say because it's rapid cooling, there is a possibility that some liquid get trapped. Okay. So that way you have a 25.8% nickel. Okay. So and solid which is alpha will have a 30% nickel. That one liquid because touching this tile and solidus, that is 31.8%. So alpha which will grow has the which is depleted in nickel 31.8%. You have still 21% nickel. Okay, but at point there will be no liquid at all liquid is freeze. So ultimately having this kind of core structure. Okay, so initially inside core you have a 46, then 40, 35 and nickel. Ultimately microstructure after it behaves like a core structure. So core structure, four color will take. So let's see. Initially this is my for low outermost. So outermost is 31.8% nickel. In that I have this one. Okay, second one that is 35.8%. Then I have this. This one is 40% nickel. Then I have inner. So that is basically 46. So in place of getting, so what I am seeing here, I am seeing heterogeneity in the alpha grains. So this heterogeneity represents my composition from center to periphery or periphery to center is not same like in equilibrium case is same. In non-equilibrium case, we are not getting same composition. So inner part will be rich in nickel and you go away from the inner part towards the periphery. Okay, the nickel composition decreases. Okay, so this structure we call as a chord structure. Okay, so this is forming chord structure. Okay, so now this is a kind of heterogeneity in microstructure. Okay, it's not homogeneous. So heterogeneity will have different. It will affect its mechanical property. So depending upon composition, I would say inner part will be more hard. If you go up outer, where depletion of nickel is, that becomes softer and softer. So you not have uniform mechanical properties. So properties get modified. So we don't want this kind of structure non-equilibrium. Now, but in day-to-day life, getting equilibrium cooling is difficult. Okay. So what they do, simply they go for non-equilibrium cooling. They melt it and solidify in a on a copper plate which is water cooled, and then they take this material and put in a furnace. Okay, and they anneal it. So when they anneal it below their melting point, so they heat it below melting point, that ingot or the material get, you heat it. Now you keep maintain for a some time, spend some time, long hours. So during that heat treatment, your atoms will start diffusing. Okay, they will move, change the respective position, ultimately go to respective position, and you have ultimate basic nickel will diffuse throughout, or copper will also diffuse in opposite direction, nickel opposite direction, and ultimately they equilibrize the alloy composition. Composition become unique, homogenized. This process we call homogenization also. This process in metallurgy we call this is a homogenization. If a chord structure, we do homogenization. Okay. Homogenization. Okay. We do this one. Regular basis generally. People working in this field, allied development. So to get the homogenized structure. So this is I explained the center of the each grain, which is first free part to be freeze, is rich in high melting point. So nickel is solidify first. At the atom will accumulate first because highest melting point. So highest melting point, material will reach, inner part will reach of that. Whereas the concentration of the low melting point element increase with position from region to the grain boundary. So from center to the grain boundary, your copper concentration will increase, where nickel will decrease. So this, then you have a kind of structure is port structure. So this give rise to the less than optimal frequency so properties. You will not get the optimal properties. To get optimal property, you need to annihilate. So like this, these are just representation of this symmetric diagram of the micrographs. Okay. From this stage, if you are cooling you are doing, you get uniform grains, homogenized grains. Here is non-homogenized grains, heterogeneity is there. So you have to get the heterogeneous homogeneous structure, you have to homogenize this one at a temperature which is well below from their melting point and for a longer period of time. So then we'll get from this structure after from here to here you have to reach. Okay. If you want to this structure from here to here, then you have to homogenize this one. Okay, homogenize this one. You have to apply homogenization. Okay. So this is about how the microstructure develop in the isomorphous system. So what I have discussed, I introduced home rule 3 rules and talk about the isomorphous systems are solid solutions of, and therefore empirical rules are applied here. Okay, and how the microstructure develop in equilibrium and non-equilibrium cases, that was I have discussed. Okay. So now I'll move to the next category of phase diagram. I'll stop this slide here and start next one. So next slide I'm sharing. That one I introduce and stop. Okay. So I'm not going to discuss that one. So this one is binary eutectic phase diagram. So in isomorphic phase diagram, those are solid solutions and they follow the empirical rules given by the Professor W. Hume Rothery. Okay, but many only they are in periodically we have a 3 alloy system only, which or 4 basically L2O3, Cr2O3 also there. 4. One is aluminum, not aluminum, gold, silver, copper, nickel, germanium and silicon, and Al2O3 and Cr2O3. Okay, but that is not in metallic case, that in ceramic case. So we generally I don't put in metallic, we have 3 only. Okay, that is ceramic case. Yeah, because those are oxides and ceramics. Okay, so in those basically they have same structure, they have same atomic radius also very close, electronegativity value also close, and same balancing. That condition for rules. But other alloys doesn't follow these 4 rules. Okay, first one is, so due to that, so there are other alloy systems. One is eutectic phase diagram. We'll discuss this one. So again, this is a binary phase diagram. There's isomorphic also binary only. Component are 2 here also, there also. But here these alloy systems are from their structure also different. Their melting point in eutectic case melting point has to be close, but peritectic melting point should be large difference. So based on that, there are 4 systems where the 4 kind of reactions I am discussing here. There are 2, 3 more are there. One monotactic, synthetic is other that we have not put here, and eutectic only we get part of slaves, but you should know what are the other 4. Okay, first one is eutectic reaction. And eutectic reaction, all these are invariant reactions. Okay, invariant reaction. They all are invariant reactions. Invariant reactions means they doesn't at that point where these reactions are occur, their degree of freedom is 0. So no variable is independently can vary. All are dependent. एक को change करोगे दूसरा change हो जाएगा. Okay, so they are dependent. So like this point here, this point is my invariant point. This is my eutectic point. Okay, in eutectic reaction, what happening? So this is a point where liquid will change at particular temperature for particular composition into 2 solid. while cooling. So one liquid will change into two kind of solid at a particular composition, at particular temperature, at a, I can say, fixed composition, fixed temperature, and fixed pressure. So when that is the case, degree of freedom is 0. eutectic निकाल लो, degree of freedom निकाल सकते हो आप. F is equal to C minus T plus 1. Here number C is 2. Number of phases, how many at this point? Liquid, alpha and beta, 3 phases are there, and plus 1. So that is gives you 0. Degree of freedom is 0. If degree of freedom is 0, for that reaction we call this invariant reaction. Doesn't vary. Okay, invariant reaction. So all these reactions, eutectic, peritectic, eutectoid, peritectoid, all are invariant reactions. Okay. Now liquid will change into, while cooling, to alpha and beta, to solids, and while heating, alpha beta change into at that point into liquid at that fixed melting point. Okay. So these reactions we call a eutectic reaction. In case of peritectic reaction, while cooling, only thing you should remember, eutectic reactions occur the element you is making for these alloys, they have a melting point very close. If your melting point is very large, there is a possibility in place of eutectic reaction we have a peritectic reaction. So peritectic reaction is the reaction where one solid alpha plus one liquid will gives you beta. Second phase. So this is my peritectic point. Okay. So symbol bhi dekh lo. This one. Okay. So this is going alpha and beta. Here we are designing this liquid like this. Okay. Here it is like this. Alpha plus beta, alpha plus liquid gives you 1 beta. Peritectic reaction. On heating you get reverse. So they are reversible reaction at that point. All reactions. And here eutectic and peritectic, liquid and solid both are involved. These two, eutectoid and peritectoid reactions, occur in solids. They occur in only solids. Whereas we have only, here is liquid, here we have liquid and solid both. So in this case, eutectoid reaction, one solid, which is, but macrostructurally eutectoid is looks like same like eutectic, and peritectoid looks like a peritectic, and they are here they are diffusion control, because in solids diffusion is very sluggish. I don't know, sluggish. Okay. I don't know if the writing is very sluggish. Okay. Very slow, I can say. Very slow. Okay. It is difficult. Okay. Diffusion of atoms is very difficult. Very sluggish diffusion. Okay. Whereas they are little faster compared to diffusion. So here is one solid gives you two solid, that is gives me eutectoid, and two solid give me one third solid. Then this is a peritectoid reaction. So peritectoid is further problematic than eutectoid also. So then we have monotactic and synthetic also, that I'm not discussing. Monotactic basically that when you have immiscibility, so they see copper nickel isomorphous, they are completely miscible. In this case, eutectic, peritectic, all these reactions are because your elements are immiscible to each other. Okay, synthetic and monotactic are there where you have immiscibility between liquid also. That I'm not discussing those things here. Okay. So with this I'll stop here, because this I could not discuss. So we'll start with your fresh this topic, eutectic reactions, eutectic phase diagram, after your quiz 2. Next week you have a reading week, and then you have a exams. Okay, online quizzes. So then when you back, so we'll start with your eutectic phase diagram. So from today's lecture, if you have anyone of any doubt, you can ask me. Okay. I have already, you can